Sriram, we're recording. Yes. Hey, welcome everyone to today's distinguished webinar series on artificial intelligence and cybersecurity. Today's talk is Intelligent Cyber-Physical Security and Resiliency for the Smart Grid, featuring Dr. Ravi Kumar Gelli, from a research assistant professor from Iowa State University. Dr. Gelli is an accomplished research assistant professor with over a decade of academic experience and has established himself as a leading researcher in cyber-physical systems, security, and resiliency for critical energy infrastructure. Dr. Gelli completed his PhD and MTech in electrical engineering at the Indian Institute of Technology, Bombay in 2016 and 2011, respectively. He was a postdoctoral researcher for 2 years at Iowa State University and 1 year at New Mexico State University. Dr. Gelli has received multiple prestigious research grants totaling over $3.6 million from organizations such as the NSF, Iowa Economic Development Authority, or IEDA, and DOE Cybersecurity, Energy Security, and Emergency Response, CSER, for his work in securing critical energy infrastructure and enhancing trustworthy infrastructure for clean energy resources. His research accomplishments have been recognized by ISU and reported in the Annual Impact Report 2022. As a result of his past and current federal and state-funded projects, Dr. Gelli has established strong collaborations with power utilities, the power industry, and national labs. Dr. Gelli has authored or co-authored over 30 IEEE transactions, conference proceedings, and book chapter publications. He's given several invited talks and tutorials at power utilities on the subjects of Phasor, information interoperability, AI and CPS security, and DERs. Dr. Gelli received the POSCO Power Systems Award for his PhD and MTech in 2016 and 2011, respectively, and the Guardian Technology Young Innovation Awards sponsored by SRISTI and National Innovation Foundation, IIM, Abu Dhabi, India. Dr. Gelli and his team are currently developing next generation grid DERMS as cloud hosted and AI integrated algorithms for resilient and economic DER integrated power and power grid operations. Dr. Gelli has designed and built advanced cyber-physical smart grid testbeds for research infrastructure integrated with cloud computing, real-time digital simulators, industry-grade hardware relays, PMUs, substation RTUs, SCADA, EMS, ADMS DERMS, and IIoT devices. The testbeds have been extensively used for RD&D prototype testing, CPS security, smart grid training, and education. His work has far-reaching implications for the energy industry, and he is currently leading multi-university, multi-industry research projects sponsored by NSF, IEDA, and DOE in cyber infrastructure and energy infrastructure RD&D. This research is funded partly by US NSF grant CNS 2010-5269 and US DOE CSER grant DECR 000016. Dr. Gelli, it's a pleasure to have you contribute to our webinar. And with that, the floor is yours.
Yeah, thank you so much, and thanks for the invitation. First of all, it's my pleasure to share our research and development activities that we carry out at Iowa State University, and thanks for the nice introduction. So with that, today I set floor for discussing intelligent cyber-physical security and resiliency aspects for the smart grid. So some of the applications that we dive through DER and DER management systems, and what is the attack surface landscape, as well as how we can combat those things with our innovative approaches. So this is
Could you share your screen again?
Okay, sorry. Can you see my screen now?
Yes. Thank you.
Perfect. Yeah, thank you. Yeah. So today's talk focuses on building intelligent cyber-physical security and resiliency aspects for the smart grid. In particular, I focus on DERs and DERMS, DER management systems, and the cyber attacks, the attack surface that can penetrate, that can impact the DER management systems, and how we can combat with our innovative solutions. So quick overview on what the research activities that we carry out which is multidisciplinary as such, focusing on power and energy systems, where we focus mostly on the modeling and analysis and system operation, resiliency, reliability, DERs, EMS, SCADA, and DERMS applications. So spanning across bulk power systems, distribution systems, and DERs and DER integration with IBRs, as well as electric vehicle charging infrastructure. So all of these things, the cross-cutting area that focuses on power system automation and how we can enhance that with uh, more defense in depth cybersecurity, because these entire systems form as a cyber physical systems, and how we can build a AI based or model based defensive mechanisms to secure the cyber physical systems. Yeah, in terms of AI, that's a very vast domain, and we have been applying multiple machine learning algorithms, deep learning, reinforcement learning algorithms to understand the cyber, which is mostly OT, operation technology, and IT, information technology. So IT OT convergence always happen in the power system as a cyber physical system. So here, so we try to explore the data diversity, data expansion, data characteristics using deep learning and model-based or physics-informed integrated approaches, so that we can come back with the more enhanced versions of deep learning-based anomaly detection, intrusion detection, or model-based anomaly mitigation, and AI-based control system. That's what reinforcement learning is, and beyond building these models, so one of the key aspects is how we can integrate this into real world systems. So that's where we need to have a cloud and grid edge computing, and the real time machine learning is the key aspect where we want to integrate these new technologies into the utility specific environments. So all of these things, unlike a traditional communication network simulation or power grid simulation, this includes the both dimensions. That's where the test beds are much more important, and I have few slides to discuss things about how we have enriched our testbed platform, which is cloud integrated as well as control, cyber, edge, hardware in the loop, CPS security testbeds for all the smart grid, including bulk power systems, DERs, and yeah, EV charging stations and all, and how we modularly and efficiently utilize our resources in terms of attacks and defensive operations and power system operations. So these are our current research grants that are supporting our students and postdocs and ourselves at Iowa State University. One of the recent activities that we focus on enhancing cybersecurity for DERs. So we are trying to build AI integrated physics-based attack resilient proactive system for distribution automation and DER monitoring and control applications. So this is getting supported by DOE Phasor, followed by National Science Foundation. This project focuses mostly on how we can build machine learning models and algorithms so that we can enhance the attack resiliency, which is one step ahead for the grid resiliency aspect in terms of bulk power systems, which is mostly wide area monitoring, protection, and control applications, and distribution systems. And the project 3 focuses on DERMS platform, but this is mostly focusing on our mobile microgrid that we have built at Iowa State University with other faculty members. So this project focuses on a software product tool that we refer to a distribution energy resource management systems for the microgrid for real-time monitoring and control of the SMA inverters and Tesla energy storage systems and other DZ units that we have at our microgrid. And all of these projects focuses enhancing energy infrastructure, cyber infrastructure, and grid reliability, resilience, stability aspects, and all. And mostly the automation and control, where you see SCADA, EMS, VAMs, ADMS, and DERMS. These are all centralized applications where they heavily rely upon the distributed, geographically distributed sensors and all. And there are multiple protocols where we will enhance their security nature, because it by nature it comes with a lot of vulnerabilities. So we'll see some of those aspects in our upcoming slides. So the flow of the presentation sets first the context of what exactly the CPS smart grid, because it has many definitions, many understandings at different dimensions, different pockets of the grid. So I'll set the path of it, and cyber attacks, cyber security, and one of the R&D contributions that we made recently about edge intelligent devices and situational awareness, and some discussion about our cybersecurity test beds, followed by conclusions. So as you all know, that we have multiple pockets, electricity producers, and the energy delivers to electricity consumers via transmission and distribution sector. And at the transmission level, if you see on the screen, SCADA, energy management systems, wide area monitoring, protection, control, they play a crucial role where they continuously monitor data from geographically distributed sensors and ensure reliability and stability of the system operation. So on the distribution side, we have distribution automation and management. And now with the inclusion of DERs, we have DER management systems and DER monitoring and control systems. So they form a underlying cyber infrastructure where they ensure reliability. And now with the inclusion of DERs, we also need to enhance the grid resiliency aspect of it. So they form again more grid support functionalities when we have large scale of PV penetration or wind penetration or energy storage system penetration to the grid. So it is very much important to have a efficient utilization of DERs. And with inclusion of DERs, there are threats as well as there are opportunities for the system operators to work upon. The threats includes different cyber attacks, because we have a lot of communication lines lay across all of these pockets, and all of them have vulnerabilities in the system. So the cyber attacks that can impact at the transmission level is much different than cyber attacks that impact on the distribution level. So it is very much important to understand the underlying dynamic characteristics and enhance the defense in depth cyber physical security, even standalone for the transmission sector or distribution sector, or together with the T&D aspects of it. So if we see statistics, this is survey conducted by SANS. SANS is one of the organizations where it continuously provide a lot of informative surveys for the IT and OT security, especially for the industrial control systems and power systems. So this was conducted in 2021, and they have received around 480 responses. And on the right side, if you see that based on their responses, their understanding of ICS threat landscape, where the sectors are most likely to have a successful ICS compromise with impact to safe and reliable operation of the process. So that was the question posed, and the participants are multiple utilities and other stakeholders in the domain, and most of them, if you see that energy sector was at the top priority, and communications, business services, engineering or control systems or IT, the things that are highlighted in red color. So where we can see some kind of interdependency of cyber attacks that can penetrate from one sector to other sector. So this actually showcases that the energy sector is at the high risk compared to other sectors when we see cyber attacks on critical infrastructures in terms of industrial control systems. So, so another question focused mostly on what would be the top business concerns aspects of it. So, if you see, the first one is ensuring reliability and availability of control systems. So, lowering risk, preventive damages, but securing connections to external systems. So, this is one of the high impacted scenario where between 2019 survey and 2021 survey, so this got rank increased and now has around 23%. They have informed that the focus should be how we can secure connections to external systems, because nowadays we have a lot of DERs, including behind the meter solar PV or wind. The grid edge technology is getting penetrated, so how we can secure those external connections. So that is one of the top business concerns when it comes to utility operators perspective. So that is where the biggest challenges of any organizations facing securing OT technologies and processes that focus on technical integration of legacy and aging OT technology with modern IT systems. So mostly utilities, substations, and utility control centers, they would be having the 5 years, 10 years, or 20 years down the line technology, and now the terms as such, those are new technologies. So it is important to find out the right balance between the new technology integration back to the legacy technology, so that we can reduce the attack surface and enhance the security nature of the modern power systems. So so these are a few more survey pointers that they have focused upon what could be the top 3 threat vectors that utilities would be most concerned with. So ransomware, extortion, other financially motivated crimes, nation-side cyber attack, and devices things, non-state cyber attacks. So these are the top 4, including integration of IT into control system networks. These are the top 5 threat vectors that utilities are mostly concerned with. So any technology, any AI-based defensive technology that should focus at least providing defense against all of these top tier threat vectors. And there were some current practices that utilities follow upon. So on the right side, we see OT connectivity. They try to do OT system to OT DMZ, so that they can make air gap security, air gap between the OT systems and the other systems, the IT and other network systems, so that at least they can have air gap security that takes place in the OT domain. But that won't be sufficient, because when we integrate more and more systems, there are so many things that needs to be taken into account, and that's where we need to see some more advanced technologies to provide defense in-depth solutions. So so there is a summary of how the other solutions that utilities can take into account. So these solutions on the right box. You can see those are some of the techniques, some of the technologies that are that are uh, uh, that are available right now, but may not be fully matured enough for utilities to install and work it upon. But these are some techniques where they can initiate deploying any available cybersecurity in terms of the cybersecurity investment for the substations or control systems, so that at least they can have more enhanced security in the pathway or roadmap. So with that, if we see in the bird's eye view, the power grid digital infrastructure is one big ecosystem. Underneath, we have advanced edge intelligent devices, controllers, and sensors. So when we try to develop cybersecurity, there are 2 different dimensions that we need to look into it. when we build cybersecurity for the entire power grid digital infrastructure, for example, SCADA or energy management systems, or DMS or ADMS or DERMS. So having cybersecurity at that level is at one dimension, and CPS security is other one, where we provide cyber physical security for grid edge technologies, which includes intelligent electronic devices or relays or any agential devices that connected the controls and sensors. So providing technologies, tailoring the AI-based solutions for the cybersecurity and CPS security has a subtle difference, and that's where we need to carefully look into it when we build solutions to it. So I'll try to focus on one key aspects of how we can enhance security aspect for the DERs, and some discussion about our novel edge intelligence devices and how we can enhance the situational awareness, including the impact characteristics and all. So the requirement is when we have a lot of DERs integrated into the systems, for example, behind the meter DERs, then the distribution utility operators doesn't have the infrastructure to understand and visibility or observation of what's happening with IT and OT traffic that happens at each behind the meter DERs or grid edge utility scale farms or wind farms or so and so. So that's one of the requirement, and we our team come up with agent devices with along with integrated environment of intrusion and anomaly detection, so that we can have a secure integration and management and operation of DERs. So on the right side, you can see the ecosystem, where on the top level, we have advanced distribution management systems and DER management systems that are there at the control center. And these technologies, this software continuously talk with different DER aggregators, and in turn, they talk with different DER clients. So here we refer the solar PV or energy storage systems, electric vehicle charging infrastructure, or wind plants with DER clients. So all of these DER clients continuously talk with DER aggregators as well as to the DERMS, so that we can have efficient DER monitoring and control system operation. So in terms of aggregators, either utilities can have their own aggregators that can be deployed either at the control center or substation level, and third-party aggregators could be deployed at a cloud-hosted applications. So the protocols that we typically use are Modbus and Sunspec Modbus between the PV inverters and DER clients that are at the edge devices, and TNP3 or ITB 2030.5 between DER clients and DERMS application. And there are other IT protocols like SSH, MQTT, Kafka. So those are other communication protocols which are in current practice with other software systems between DER clients and DER aggregators, as well as with the DERMS. So if we see the underlying payloads that exchange or DER measurements, which includes state data, voltage, current, P and Q, frequency at the point of common coupling that we measure, and solar irradiance, modular temperature, so many other aspects that there are more than 100 parameters from each SMA inverters that we can measure continuously. So typically the time scale is based on SMA inverters, it's like 30 seconds, but here we tested at every 1 second with our hardware in the loop simulations. So then there are different advanced grid support functionalities or control systems, where we can have set points control, volt watt control, volt var control, droop settings, or ramp rate settings. So all of these things can be sent with different time intervals from the DERMS to the DER clients. And now if you see, all these communication networks could be vulnerable and have different attacks like data integrity, denial of service, timing attacks, replay attacks, and man-in-the-middle attacks. So that's where we need to enhance the stealthiness of cybersecurity for measurement signals and control signals, and together, so that way it becomes more comprehensive solutions for that. So here on the left side, you can see what are the different cyber attacks that could be foreseen in our DOMS infrastructure, integrating attack, data integrity attacks, malicious DR commands, ransomware attacks, DOS, DDoS, and on the right side you can find out different cybersecurity solutions, device level cybersecurity, network level. So here I focus few on intrusion anomaly detection prevention systems, and beyond this active, so we also need to have some kind of good practices where standards like NUCSIP, C2M2, and SEAM tools, which is like a security operations center. So we also work with one of the open source security operations center, which is a Security Onion, where that actually provides more enhanced abilities to monitor and do deep inspection about packet analysis on all the cyber logs. So as I mentioned, so it is important to find out what could be the different communication protocols so that we can tailor our technologies to that. So there are set of DER communication protocols, including Modbus, Unspec, Modbus, IEEE 2030.5. So those are the top tier communication protocols that are recommended by California Rule 21 guidelines. And IC 64850, it provides information model. So that is also tying up with Sunspec Modbus. There were continuous efforts happening in that regard. And DNP3, OpenADR. So those are other communication protocols. Typically, DNP3 is a protocol that is available across US cooperatives as well as distribution and bulk power system. In OpenADR, we see other parts in the worldwide. And these are the communication protocols. And when any DR integrated to a grid, we need to form or we need to follow strict guidelines which are defined in 1547 2018 grid interconnection standards. So on the right side, you see there is the mapping of these communication protocols into our hierarchy between DERMS and DR aggregators and some plant controllers and PV wind. So this is one different topological infrastructure that could be in practice. And every protocol, as I mentioned, have strengths and weaknesses. So this table is one of the efforts by Sandia National Laboratories, where they have identified what could be the vulnerabilities, what could be the strengths, and also that we can actually see and map these things when we devise intrusion or anomaly detection systems using the available SNOT or Suricata engines or any AI-based techniques. So this is our one of the architecture when we work with collaboratively with other partners. So this work was initiated in the DOE SATO project, which was recently completed. So on the left side, you see those are the inverters and intelligent devices, so connected with the field area network. So this infrastructure is representative of our testbed conceptual architecture, where we conducted studies and all. And on the right side, it's a SEOP, solar energy optimization platform, which can be considered as a DR aggregator, and IADS master, which is intrusion and anomaly detection system master, where it continuously collect cyber as well as grid data or any payloads from EADs. So the main aspect here is the EID, which is one step ahead of any current available devices. And the main purpose of this EID is to provide interface between DERs, which are the like behind the meter DERs, and to the cloud, and optimize latency and autonomy nature of it, and move data and processing closer to DER. So here we try to bring the edge computing so that we can have edge computing based analytics at the edge level, and they also provide more information rich data sets to the cloud so that we can have more enhanced applications to it. So this is one of the real utility distribution grid model, where here I show only one substation. You see on the tail of it, and the substation a feeder head penetrated across the city, where the red dots focuses upon loads, and on the green dots, those are like 766 DERs, behind the meter DERs. Those are heavily integrated into this high PV integrated feeder. So on the right side, you can see the number of PV systems like 767, and we model 766 because one of them are not fully available, the data set. And the maximum PV generation that was seen is 3.8 megawatts, and maximum instantaneous PV generation was 236%, where there was reverse power flow happened from the DRs to the substation and sub-transmission systems level. So we first, so this is closely work with Arizona State University, and we first focused mostly upon how we can journalize this entire distribution system. So we come up with the 5 zones, so that way we can have more impacted studies on each zones. And these things were first available in SIME, and our students modeled that in OpenDSS, and then we converted the models towards to the ePhasor mobility so that we can have a real-time simulation, and the model is quite extensive in terms of number of nodes, number of loads, and DERs, especially high PV integration. So this can be very good representation when we tested our systems. So this is our experimental test bed environment, where we modeled all of those distribution grid model in OpenRT, and then the green boxes, those are grid voltage and grid voltage at DERs and feeder nodes. Those are like sensor nodes. Provides to the green boxes, which are 1547 smart inverter operation modes and DER inverter. So those are our new proposed models in real time. And those models, a high level representation was given, circuit model, state space model, and transfer function model, so that we can test real time DER in the loop operation. At the same time, we integrated the purple boxes, the EID and IADS, so where that intent exchange information to utility level DOMS platform. And so once the CPS system operation is set, then we had attacks injected, and then find out cyber impact characteristics, as well as some kind of defensive mechanisms to that. So this is a blueprint of our edge intelligent device, where the communication modules, grid application modules, cybersecurity modules, we categorized into 3 of them, so that we can do multi-threading, multi-processing. So it becomes more real-time operating system that can work in tandem with DERs, and as well as interact continuously with upstream applications like DERMS. So we have, and our team actually collaborated. Foundry is one of the vendor partner, and they have focused mostly on the commercially off-the-shelf technologies. So including PLC Next and CRAO. So on the top right, two PLC Next and CRAO are the 2 technologies that were attempted, and bottom we can see multiple other technologies that can also be utilized. And and these things actually showcase that our algorithms can work in tandem with the edge intelligent commercially off-the-shelf devices. And for the scalable testing, what we did was we actually built a AID software that is Dockerized and Kubernetes based, and we used Raspberry Pi as one of the hardware that is actually integrated into our system. So we use multiple Raspberry Pi systems, and we connected that with SMA inverters, and we launched those EAD softwares into it. And so those are like a hardware, a software together. And we also had those, because those are Dockerized, so we deployed them across the multiple VMs in our test bed so that we can test more scalable system studies. So this is more detailed information that could be uh, well understood, that uh, PLC Next as well as the CREO, different intelligent devices that can be designed with different capabilities. Because when we design all of those things, it is also important to see the cost effective as well as affordable solution, and it should be more rugged in nature. So all of these non-technical aspects are important when we move towards more deployable edge intelligent devices. So this showcases the integration aspect. So on the bottom right, we can see the Oplati, and uh, it has all the grid models for all the grid and system studies, and that we have used Modbus server groups. So here we have had I think 10 DERs for one server group. So like that we have plenty of them around. I think we have 77 at the end to capture all the 766 DERs. And so this aspect provides real-time communications from Oplati via Modbus to our VMware infrastructure, where we have all of these are like virtual missions, where each virtual mission have multiple Dockers that runs in real time. So we can establish a cyber topology across all of these things. So this is another blueprint of how the Oplati, the grid models that look like. So for to DOE, we actually demonstrated very stealthy potential attack, that is attack on one of the control signals, which is volt war control. On the right side, the blue curve, that is a default IEEE 1547 2018 volt war curve. So so on the so it has voltage low limits like 0.95 to 1.05. That's a typical dead band. And if we have less than 0.95, then reactor power must be injected so that it can support voltage. And if we have more than 1.05, then reactor power should be consumed so that it can reduce the high voltage nature of the grid. So that's a typical volt war with reactive power interactions. So now the attack, so this V1 Q1 or V2 Q2, V3 Q3, those are the set points that are typically sent from the DERMS to the DR aggregators to the edge devices. So now if any of these things get impacted, for example, here on the top, we actually launched attack where we manipulated by the slope of the signal on the left side as well as right side, and increase the dead band. That's one potential attack vector, and see and tested that impact characteristics on the real utility distribution grid model. And second attack scenario that could be very interesting, that we just toggled the queue aspect of it. In this case, when the system experiences low voltage, like less than 0.98, for example, then it's ideally it must inject power, reactive power, so that it can boost voltage profile. But because of this new attack vector, so the inverters that see when there is a low voltage, then it further consumes reactive power, and vice versa, when there is a high voltage, it injects reactive power. So that actually leads to instability in the distribution grid. So, these are the quick results aspects of it, where on the left side you see A and B are typical system operation, where this is our PV profile uh, uh, with the 766 PV profile, and on the top I showed voltage profile across all the DERs and all other distribution nodes, where because of this DR penetration, they have high voltage scenario. So that's where we need to inject volt-var control into it. So the B actually showcases a typical volt-var control operation, so that it brings the voltage profile within the threshold band. And the DEF shows that when we launch the attack that was seen in the C, that instead of blue curve, if we have a red curve, that's a manipulated attack vector, then how the Q injection changes and how the V impacts, and at the F plot showcased what is the uh, cumulative impact between the no attack and attack on the volt-var control system. So this is another impact scenario where I showed like the C shows that attack vector, where the A and B again the same system operation, and when we have the attack vector that was seen on the C, the impact is clearly shown on the D and E, where for example, if you see when there is a high voltage, the reactive power in the B supposed to be negative, which means that it needs to consume when there is a high voltage profile. But on the other hand, in the E case, that is during attack scenario, it actually showed positive, which means Q got injected into the system. So which further destabilizes the voltage profile, and which we also seen voltage instability. And there's a lot of impact that was seen on the plot F, where between no attack and high attack. So this is our software that we developed, where showcased the real-time monitoring and control of our DERs. So this actually provides cyber-physical situational awareness of it. So on the red plot, you can see the launch of VVC attack before and after, so that the system operators can quickly identify so what could be the impacts that are happening. They may not identify this is an attack that is happening on the volt-var control, but they can see on this the impact of it. And we have another intrusion anomaly detection charts, where it actually showcases that the different pointers where the manipulations might occur. So these are the four plots where voltage, Q feedback, and IRMS and P feedback. So if you see the impact of attack happen only on can be seen on voltage profile and Q, but and we don't see that major impact on the I and P. So it is so this actually showcases that it is must to capture all the different measurement signals, so that we can see the comprehensive characteristics and attack natures and across the DERMS platform. So this is one of the other one which we have been focusing on, EV charging infrastructure. So the DERMS platform, TND, DERs are more or less similar. The EV charging infrastructure changes at the edge level of it, where the aggregator talks with operator, is a EVCS operator, and it has multiple EV charging stations where they use OCPP protocol, and we started this exercise I think this year as part of our DOCASA project, and we have had a good impact on the launching attacks and uh, detecting anomalies, intrusions in the EV charging infrastructure. So this is our recently submitted transactions in the IEEE Smart Grid, where it showcases the overall flow of anomaly detection using LSTM by LSTM based models for providing more defense for the electric vehicle charging infrastructure. On the bottom, you can see we have EVCS management system included with our mostly built in the Oblati as such, and then we have built API to autonomously generate synthetic data sets that includes both system related events as well as attack related events, and then a typical feature extraction, data pre-processing, data loaders, and training data set and testing data set is a split when we try to develop deep learning based models. And we have made hyperparameter tuning a rigorous by LST models and multiple deep learning models across all of these data sets. Once we ensure we have met accuracy limits, then the trained model, then we deploy in the real time, and then we again test it in the real time in the loop by injecting a new measurement, a new control signals in the loop. So, as of now, I have been explaining multiple concepts with where the test beds play a crucial role aspect of it. So this is our one of the infrastructure snapshot that are available at our state university, where you see the first three racks focus on the grid related devices, including relays, PMUs, and OPLAT real-time simulator. On the right side, those are our VMware-based on-premise private cloud infrastructure, which is accessible online, where we have installed multiple EMS, DERMS, and WAMPAC, and many of software modules, and the cyber topologies, so that we can have more scalable studies for this attack and defense operations. So this actually showcases the information architecture of the test bed, where physical system level and CPS interface level and cyber system level. The most interesting part is how we optimally utilize and virtualize the available operating system, and how that gets integrated in with the real hardware, which is a Swagger with different protocols, IC 6150, and the Siemens automation system with the DNP3 protocols, and 37118 for the PMUs, and Sunspec Modbus is another one. So this infrastructure is for the bulk power systems, and there is similar one which we have for the DERMS platform. And the right side, you can see we have multiple SCADA EMS from the Siemens, PowerTZ, and eTerra. And in terms of DERMS, we have been working closely with EPRI, and we ourselves are building a grid DERMS platform. So right now it's in the development stage. That's where I cannot show multiple aspects of that. So this is our ISU mobile microgrid infrastructure. On the left, you can see two SMA inverters. This is a capacity of 15 kilowatts, where we, after prototype testing on the test bed, so on the right side, you can see the Raspberry Pi, the digital devices that is connected to one of the microgrid infrastructure routers, where we continuously monitor the data from SMA inverters and Tesla energy storage systems and DC, and then transmit the data to our test bed, where the DERMS platform is available. And then, so these things we actually use for realistic field prototype testing, so that we can have more robust in terms of testing the verification of performance on the AI-based algorithms. So this is one of the things that we have deployed, a intrusion and anomaly detection tool in 2020, and one of our DOE SEECS project, where there are multiple substations, where the E substation, sensor 1, sensor 2, sensor N, those are the blue nodes. Those are our EID sensor nodes that are deployed, and master node deployed at the SCADA master. So where these sensors continuously monitor ingress egress traffic, and if there are any intrusions detected. So for example, this is a pen testing under the surveillance of system operators. So this is one of the field testing we have successfully tested with the real distribution substation infrastructure, where there is a dummy substation they have created for us, so that we can have pen testing. You can see on the bottom that the intrusions that were detected and then it got transmitted into the SCADA master. So beyond those R&D, we also use the test bed for education purposes, and our students extensively utilize. We have thousands of virtual machines that are available, and this is our test bed infrastructure, which can be remotely accessible at this link. And we also share some of the infrastructure for the federated based test bed when we work with EPRI and Arizona State University and other national labs in our current and past projects. So these are some screenshots about our CPS security training, which we usually conduct using a test bed to multiple utilities and multiple universities and at different conference venues and all. This is one of the success stories that we could accomplish, where we conducted a 2-day training in India. So where the around 30 testbed environments, where each environment has 15 virtual machines. In total, around 450 virtual machines got utilized for CPS security training between for the SCADA and EMS and VAMPAC systems. So I take a pause here, and there is a demo if required. It's available to share with the YouTube, but I'll take a pause for any question and answers. And so before that, so the talk focused on the and the the aspect of attack surfaces continuously evolving into IT and IoT and cloud infrastructures. So we need to ensure the protocol and information security at the terms level, and as such we need to have more defense in depth solutions. So here I was not completely focused more detailed aspects of what we do in the AI and machine learning based, but if there are any questions, I would be happy to discuss those things. Yeah, thank you.
Thank you, Dr. Gelly, for your presentation. Appreciate for your time today, this morning, for us. And so I think it's time for Q&A. I think we'll gather some questions, and maybe I'll start with a question. How do you see there is more and more DER penetrations are happening, and from your perspective, from your discussions with vendors, and in terms of, are there any agreement in terms of communication protocols? Which type of communication protocols do you see, that's more robust against attacks, or what is your perspective, and how do we see going forward, looking at the IEEE 1547 guidelines, and any thoughts on that?
Yeah, that's a very good question. It's very broad. So yeah, sure. So we had close collaboration with Alient Energy, which is one of the distribution utilities in Iowa, and close collaboration with Duke Energy, which is the generation, transmission, distribution. So when we so some of these utility partners, including Alient or Duke Energy, or another utility partner in our DOE SATO project. So where typically they use currently AMI infrastructure to get and they install net meters to get information at least for every 15 minutes or 1 hour. But on the other hand, they also put investment towards deploying the more DER specific communication protocols, which Sunspec Modbus is one of the communication protocols, and IEEE 2030.5 is another communication protocol. So where Sunspec Modbus communication protocol happens between the smart inverters or EV charging station or any IBR related or energy storage systems. So that is where Sunspec Modbus communication has been in the discussions, and even in the California Rule 21 also recommended Sunspec Modbus communication. But on the other hand, it really uses Modbus communication protocol, which is plain text and which is not secured. So it is very much important to have a built-in security, or security by design is another aspect that utilities actually looking into it. So other aspect is ITLB 2030.5, where it is designed for more remote operations between multiple solar plants or multiple EVCS plants, and when we integrate that with field scale to the DERMS platform. So most of the utilities, they still have ADMS kind of solutions, and they're still looking for either from the same vendor, integrated DERMS, or different vendor with the DERMS platforms. But mostly built-in cybersecurity is one of the key aspect that we always hear from the vendors or utility partners.
Great. I think we have lots of questions coming up here. Could you comment on important consideration one should make? Example on grid topology, DER penetration, and types when mathematically modeling realistic stealthy FDI attacks.
Yeah, sure. So in terms of the FDI attacks that we can see in different aspects. So one is when we conduct completely on the grid simulation level, where we data integrity with different pulse or replay, or different stochastic nature of manipulations that could be launched at the measurement signal, as well as the communication control signal aspect. And when we, like in academy also, when we use simulation tools, typically we keep all of those manipulations or all of those experiments we do in the simulation environment itself. But then that may not capture the realistic characteristics, including latency, network congestion, and how we can see in real world. So that is where we need to see different communication topologies. Maybe let me go back to the terms topology here. Yeah, so this is one topology of it. So and if we see, when we speak with utilities, they have direct connections from the DR management system and to the DR clients, and they completely avoid any aggregators, including utility aggregators. So that's one topology of it. And the other topologies could be utility aggregator happened between DERMS and client, DR clients. Another topology could be these aggregators are between the EMS and DERMS directly connect with the client. So when we have different communication topologies of this nature, it is important to have more realistic communication topology in the testbed infrastructure. So that could be envisioned either by typical simulators like NS3 or Mininet kind of simulators, or we can also envision that with for example, we use here VMware infrastructure, where it actually provides all the virtual networking capabilities. So where we can launch any firewall rules, firewall routers, or any Cisco images directly in the system, where it actually does the cyber emulation aspect of it. So when we have these three or four, like when we have a complete realistic cyber emulation and grid simulation, or cyber simulation and grid simulation together, or only grid simulation. So I think these are the topologies that we need to consider it when we launch any false data injection attacks and all. And there is a lot of literature upon how we can tailor the data integrity attacks so that can satisfy H equal to XC, that is actually for the state distribution for bulk power systems, but that also applies for the distribution system, where if we randomly change something, that can be easily detected by bad data detectors. So the stealthy nature should be such a way that the bad data detectors should be bypassed, and then the attack can be successfully penetrated. I think doing that makes more sense, so that we can have more robust testing when we do any machine learning or deep learning based anomaly detection.
Thank you. And then we have another question. Do you think it can be possible to automate some human-based control management behaviors within such a CPS structure? I mean, what are the limitations towards total autonomous CPS in grids? What are the advantages or disadvantages for such approach?
Yeah, that's very good. Actually, we had a recent discussion with one of our utility partners about that. So where we can go for more autonomous kind of operation, as well as keeping flexibility to keep human in the loop operation, because we don't want completely always autonomous operation in the systems. So when it comes to deep learning aspects of it, so it is very much important to see the trained models or tested models when we put them in the streaming based data input, as well as in the real-time feedback loop. It must comply some real-time guidelines in terms of timing properties or latency properties as such. So okay, sorry, I got disturbed with one of the messages. So it is important to test real-time machine learning in the loop, and on the other hand, we also been working on deep reinforcement learning, where unlike the deep learning where we provide data sets directly to train and test, so here we actually provide entire environment as an input to it. So with the data sets, we might miss some of the characteristics from the environment, and those deep learning models might have more false alarms. So to combat to address that problem, what we were trying to do is we integrate directly the environment into a deep reinforcement learning architecture, where deep reinforcement learning provides a kind of agent that we will train continuously for the policy, and it continuously interact with the grid environment or cyber-physical system environment. So this actually provides more trust and more reliability to move towards deploying deep learning or deep reinforcement learning into DERMS or such operations. But utilities are really looking after autonomous operation in a single short answer. And they also like to have a flexibility to move for human in the loop whenever there are different requirements.
Thank you, Dr. Gelly. And I think in the interest of time, I think we're going to close the webinar. And I appreciate for you spending your time this morning with us. And, as a token of appreciation, you will receive a nice plaque from UND and a letter signed by our dean. And thank you so much for your time. And we look forward to working with you.
Thank you so much. Thanks for the opportunity. And if there are any more questions, always shoot an email to me, and it's available on the link.
Yeah, we will also make the recording available on our YouTube channel, so we'll send you the link as well. Yeah.
Yeah. Thank you so much. Have a great day. Thank you.
Yeah. Happy holidays.
You too.